Before we tune Spark performance in Databricks, we need to understand how Spark actually runs. A Spark application starts with your code. This code can come from a notebook, SQL, or PySpark. When you submit the job, the driver becomes the coordinator. It analyzes the work, creates the execution plan, breaks the job into stages, and schedules tasks. The worker nodes provide the machines where the work can run. Inside those workers, executors process data in parallel. Each task works on a partition of the data, and the final results are written to Delta Lake, storage, dashboards, or downstream systems. The key idea is simple. Spark performance makes more sense when you understand how the engine runs. Let us start with the core building blocks of a Spark cluster: the driver, the worker nodes, and the executors. Your code is submitted to the driver. The driver runs the Spark application, creates the plan, schedules the work, and coordinates the executors. Worker nodes are the machines in the cluster. They provide CPU, memory, disk, and network resources. Executors are processes running inside those worker nodes. Executors are where the actual task execution happens. This distinction is very important. Workers are the infrastructure. Executors are the processing engines inside that infrastructure. If you confuse workers and executors, Spark tuning becomes much harder. The driver is the brain of the Spark application. When you run code from a Databricks notebook, SQL command, or PySpark script, the job is submitted to the driver. The driver creates the Spark session, builds the logical plan, creates the DAG, breaks the work into stages, and schedules tasks for the executors. But remember this clearly: the driver does not process all the data in parallel. That heavy work is done by the executors. The driver coordinates. The executors execute. That is why an overloaded driver can still slow down the whole job. If coordination becomes slow, the entire application can suffer from bottlenecks. Now let us look at where the work actually runs. A worker node is a machine in the cluster. It provides resources like CPU, memory, disk, and network. Inside each worker node, Spark can run one or more executors. An executor is a JVM process that receives tasks from the driver. It has task slots, uses memory for processing and cache, and returns results back to the driver. So when Spark runs in parallel, it is really the executors running many tasks at the same time. More executors and more task slots can increase parallelism, but only if the data and resources are balanced. Worker nodes provide capacity. Executors use that capacity to execute the work. Spark transforms your code into jobs, stages, and tasks. A job is created when you trigger an action, such as write, collect, count, or save. Inside that job, Spark creates stages. A stage is a group of tasks that can run in parallel without needing to reshuffle data. When Spark reaches a shuffle boundary, for example during a group by or a join, it creates a new stage. Tasks are the smallest units of execution. Each task usually processes one partition of data on one executor. So the mental model is this: actions create jobs, shuffles split jobs into stages. Stages contain many tasks. This is exactly why Spark UI shows jobs, stages, and tasks separately. Partitions define how Spark splits the data for parallel processing. Think of a dataset as a large collection of records. Spark divides that dataset into partitions, and each partition can be processed by a task. This is powerful because many tasks can run at the same time across executors. But partition quality matters a lot. If partitions are balanced, work is distributed evenly and the cluster is used efficiently. If there are too few partitions, Spark has limited parallelism and resources may stay idle. If there are too many tiny partitions, Spark creates too much scheduling overhead. And if partitions are skewed, one task may receive much more data than the others and become much slower than the rest. Tasks process partitions, so partition quality directly affects performance. Spark performance is not only about code, it is also about cluster resources. CPU affects computation speed. Memory affects caching, joins, aggregations, and shuffle tolerance. Local disk matters when Spark spills data or uses local storage during execution. Network matters because shuffle moves data between nodes, and poor network performance can make large joins and aggregations slower. Worker count affects parallel capacity. Autoscaling helps adjust resources based on workload, but it must fit the job pattern. Driver size matters because the driver coordinates the application. Worker type matters because different machines provide different CPU, memory, disk, and network characteristics. The goal is not always the biggest cluster. The goal is the right-sized cluster for the workload. Here is the end-to-end execution flow in a simple way. First, you write code in a notebook, SQL, or PySpark. Second, the driver builds the plan, analyzes the logic, optimizes it, and creates stages. Third, executors run tasks on partitions in parallel. Fourth, if the job needs data movement, Shuffle redistributes data between stages. Finally, the results are written to Delta Lake, cloud storage, dashboards, or other downstream systems. This flow helps you debug slow jobs, understand Spark UI, and make better tuning decisions. When you understand the execution flow, performance tuning becomes much easier. Let us recap the Spark architecture mental model. Your code goes to the driver. The driver plans and coordinates the work. An action creates a job. That job is split into stages. Stages contain tasks. Executors run those tasks in parallel, usually processing partitions of data. Finally, the results go to Delta Lake, storage, dashboards, or downstream systems. This foundation helps you understand Spark UI, Shuffle, skew, joins, and performance bottlenecks. Before you tune Spark, first understand how the engine thinks.